and action.
Okay, in this video, we're going to talk about what is in the filtrate and how filtrate processing occurs. Okay, so we said that blood was going to enter the glomerulus, and because in the glomerulus the hydrostatic pressure is greater than the osmotic pressure all the way through, and any opposing pressures, then there's going to be filtrate produced all the way through these capillaries. And that filtrate is going to collect here in what's called the capsular space, which is the space between the visceral layer of the glomerular capsule and the parietal layer of the glomerular capsule. Okay, now that filtrate is mostly water, but it also contains small solutes. Okay, so there is a specific size cutoff of 3 nanometers that will determine what substances can pass through. Also, the basement membrane of the filtration membrane is negatively charged, and that tends to repel negatively charged substances that might be close to that size. So if we think about comparing filtrate to plasma, filtrate and plasma both have water. They both have things like sodium ion, chloride ion, potassium ion, glucose, amino acids. But some things that are larger will not get out of the plasma, like albumin and other large plasma proteins. Okay, so that's why diagnostically it's important if we see proteins showing up in someone's urine, because that tells us that there's something wrong with the way that we're making the filtrate, because normally those substances shouldn't be able to get through. Something else that should not be able to get through the filtration membrane is erythrocytes and other formed elements. So if you see formed elements in the urine, that doesn't always mean that there's something wrong here with the filtration membrane, but it can. So those are kind of warning signs. When you see those larger substances appearing in the urine, those are warning signs that there may have been some compromised structure to the filtration membrane. Okay, so we're going to assume that filtration is working properly and only water and small solutes are getting through. But those small solutes are basically going to be at the same concentration in the filtrate as they are in the blood. And that would be a problem if we were going to let all of that filtrate just go through and become urine. We would lose too much of our water from our plasma and also those solutes. So we're going to have to invest some time in processing this filtrate as it's moving through. Okay, so you'll notice that compared to the video where we looked at the anatomy, I've drawn in the remainder of the efferent arteriole, and now you can see we have this kind of pinkish purple structure that's kind of following the contours of the renal tubule. And that structure is a representation of the peritubular capillaries. Okay, so we're kind of thinking of our theme of borrowing from the blood. Things that are borrowed from the blood have to be able to return to the blood. Okay, so if we are having materials filtered and we want those back, they're going to leave from the glomerulus and they're going to return to the blood by going into the peritubular capillaries. So again, remember, the peritubular capillaries are like the venous end of our capillary in a typical capillary bed. So this is where our reabsorption is occurring. All right, so if we think of reabsorbing as far as tubular reabsorption in urine processing and urine formation is taking material from the filtrate and returning it to the blood. So each section of the renal tubule is going to have different responsibilities associated with that and different capabilities. Now, based on the anatomy of the peritubular capillary, we already know that this is the most active area for reabsorption. And we know that because this is the only section of the renal tubule that has an epithelium with microvilli, so more surface area for reabsorption to occur. And we didn't talk about this previously, but you may have noticed in your readings that these cells have more mitochondria and larger mitochondria than other renal tubule cells. So that's telling us that there's more energy needed and there's more active transport going on here. So this is our main area for reabsorption. Okay, so what kinds of substances are we going to reabsorb here? Okay, we're going to reabsorb sodium ion, we're going to reabsorb potassium ion, chloride ion, glucose, amino acids, and water. Okay, now I do want to talk about the glucose and the amino acids for just a moment, because we're going to see that there are other places where we can reabsorb ions and water, but there is no other location in the renal tubule where we can reabsorb glucose and amino acids. Okay, so the key to reabsorbing all of these substances in this location is they have to be at normal levels in the blood. As long as glucose is at normal level in the blood, we'll have enough transport proteins to reabsorb all the glucose that could be in the filtrate. However, if you have a patient who has unregulated diabetes, one of the signs of unregulated diabetes is that glucose will appear in the urine. The reason the glucose is appearing in the urine is because the amount of glucose in the filtrate is exceeding the capability of the PCT to reabsorb the glucose from the filtrate. And that is referred to as exceeding the transport maximum. So the transport maximum, you'll sometimes see it as a capital T with an M as like a little add-on. That term refers to the kind of the upper limit of how much of a substance can be reabsorbed in one location. And it's based on the number of transport proteins that are in the epithelium of that section of the tubule. Okay? All right, so the only place where we can reabsorb glucose and amino acids is here in the PCT. We can't absorb ions and water, and we'll have other opportunities to reabsorb those as well. Okay? So as the filtrate is moving out of the PCT and into the descending limb of the nephron loop, it should have no glucose and no amino acids remaining in it, and the amount of water and ions should be decreased. So as it's moving into the descending limb, we're going to see that the only thing that is reabsorbed in this section of the tubule is water. Okay, so we're going to have water being reabsorbed here, and there's a gradient in the kidney that attracts water out as the filtrate is moving through. And this is going to create a situation where the filtrate is going to be highly concentrated by the time it gets to the bottom of the U shape of the nephron loop. Okay, as it starts to move further, now the permeability of the tubule to water will end, and the reabsorptions that are going to take place now are going to be ions. Okay, so we'll have sodium ion, potassium ion, and chloride ion. Sometimes you'll see in textbooks that they'll talk about salt reabsorption happening here, and they're talking about sodium chloride, potassium chloride as the salts, okay? And so that movement of ions into the blood is going to give us the reabsorption of those substances, okay? Now, if the person is in water balance, this is the last section of the renal tubule that will be used to process the filtrate. Now, what I mean by person being in water balance is that they're in a situation of fluid homeostasis, and the amount of water that's coming into their body is equal to the amount of water that's leaving their body. As long as that's the situation, then the processing of the filtrate will be finished by the time the filtrate gets to the end of the nephron loop, and no filtrate processing will occur in either the distal convoluted tubule or the collecting duct. Okay, and in that situation, the person would be eliminating dilute urine, meaning that it's urine that has the excess of substances that we want to get rid of, but it's in a substantial quantity of water. Okay? We'll see that that will be different if a person is not in water balance.